Chapter 6. In this chapter, we discuss few widely used continuous type of probability distributions. In Chapter 5, we learned about different discrete type of probability distributions. Similar to that, when your random variable is continuous, we have well-defined and widely used probability distributions. So under these continuous probability distributions, the first one that we are going to look at is called the uniform distribution. If you can remember, in Chapter 5 also we had the discrete case of the uniform distribution. This is similar in continuous case also. Now your random variable is continuous. According to the definition, a random variable has a uniform distribution and it is referred to as a continuous random variable, a uniform continuous random variable if and only if its probability density is given by this equation. You can see that the random variable x can have values within the interval alpha and beta, where alpha is less than beta. Therefore, the two parameters of the uniform random variable is alpha and beta. You can write this as x follows uniform distribution within the interval alpha and beta. Let's look at the graphical interpretation. If you look at this graph, your x-axis contains the interval from alpha to beta. Since the total probability is 1, the property of the uniform distribution is that all the values within this given interval alpha and beta should contain the same probability. This is similar to the discrete case. In discrete uniform distribution also, we saw that all possible values of x should have the same probability. Therefore, we divide the total probability 1 by the number of possibilities in x. In the same manner, when it comes to the continuous case, we consider all the values within this given interval alpha to beta. So all these values should have the same probability. In order to achieve that, we divide 1 by the length of the interval. The length of the interval is beta minus alpha. So all the values within the interval alpha to beta will have this value 1 over beta minus alpha. So that is exactly what you see in this equation. For all the values within alpha and beta, the probability is 1 over beta minus alpha and it is 0 elsewhere. Now with the definition, we can find the mean and the variance of the uniform distribution. The mean is the alpha plus beta divided by 2, that means the midpoint of the interval, and the variance as 1 over 12 beta minus alpha squared. Let's try to prove the mean and the variance. First, we'll start with the mean. If we use the definition, the expected value of x, we integrate our function which is fx dx. It should be multiplied by x. So this is the definition of the expected value. Ex is x fx dx. You integrate over the support of x. Our support is now from alpha to beta. Okay, so let's substitute our function. Fx is 1 over beta minus alpha. Since beta and alpha are constants, you can take it outside the integration. Then we have alpha to beta just x dx. Now take the antiderivative. We have 1 over beta minus alpha outside the integration. The antiderivative of x is x squared over 2. Evaluate it over the support alpha to beta. Now this will be 1 over beta minus alpha, and then when we evaluate x at beta and x at alpha, you get beta squared minus alpha squared divided by this 2. Okay, so this is the difference of squares. You can expand it as beta minus alpha and beta plus alpha. So this beta minus alpha cancels out and you end up with the expected value of x as alpha plus beta divided by 2. Okay, so that is the proof of the mean of the uniform distribution, which is alpha plus beta divided by 2. Now let's move on to the variance. In order to find the variance, you can use the computational formula, which is the expected value of x squared minus expected value of x whole thing squared. We already have Ex now, which is alpha plus beta over 2. And by squaring the whole thing, you can get the second term. Which means first we have to find the expected value of Ex squared. Again, we use the definition, which is x squared times fx dx. So this is the second moment, right? We evaluate it over the support of x. So in our case, that is from alpha to beta, x squared 1 over beta minus alpha dx. So again, let's take beta minus alpha out of the integration. We end up with x squared dx. Now let's evaluate this integration. We have x to the 3 over 3, evaluate from alpha to beta. Okay. Now what do we get? We have beta to power 3 minus alpha to power 3. Okay. Now you need the difference of cubes. Okay, the difference of cubes, if you can remember, that will be, okay, so let's start writing beta minus alpha, our term outside the integration. Now expanding beta to power 3 minus alpha to power 3, that will be beta minus alpha. And then you have beta squared plus alpha beta plus alpha squared over 3. Okay, so this beta minus alpha will cancel out, and we end up with beta square plus alpha square over 3. Now let's use this in our variance computation formula. So our Ex square is beta square plus alpha beta plus alpha square over 3. Then we have to subtract the square term of the mean, which is alpha plus beta square over 2 square, which is 4. Now let's expand this. We have beta square plus alpha beta plus alpha square over 3. That's our first term. You subtract. Let's expand this quadratic form. So I have alpha square plus 2 alpha beta plus beta square. Divide this by 4. Okay. Let's try to simplify this. Okay. It's better if we take the common denominator. Okay, so we'll do it as a single step. Okay, the common denominator will be 12. So you have 4 times beta squared plus 4 times alpha beta plus 4 times alpha square. Then you have to multiply the second term by 3. So with the negative, you have negative 3 alpha squared, negative 6 alpha beta, negative 3 beta squared. Okay. Now let's try to cancel out the common terms. We will end up with 4 beta square minus 3 beta square. We have 1 beta square. Then we have 4 alpha square minus 3 alpha square. So we end up with 1 alpha square plus 4 times alpha beta minus 6 times alpha beta. So which will end up with negative 2 times alpha beta divided by 12. I hope this is clear to all of you, this expansion and the simplification. Now if you look at this, this is none other than the beta minus alpha all things squared, the quadratic form. If you expand this, you can get beta squared minus 2 alpha beta plus alpha squared over 12. So this is exactly the variance we wanted to prove. Beta minus alpha whole thing squared divided by 12. Okay. Now let's try an example. Okay, so let's say the waiting time for a bus is uniformly distributed in the interval, uniformly distributed in the interval let's say 10 to 20 minutes. So the waiting time is our random variable. Okay, x is the waiting time. According to the content, it says it is uniformly distributed in the interval 10 to 20 minutes. So you can write it as x follows uniform or just u within the interval 10 to 20. When we have the continuous densities, we usually use the open brackets rather than the square brackets. Okay. Now, if x follows the uniform density with 10 and 20, you can see that our alpha is 10 and beta is 20. Okay. And you can, if you want, you can interpret this graphically also. Now, what is the mean waiting time? What is the mean waiting time? We already know the equation, mean waiting time, that is the expected value of x, that is alpha plus beta divided by 2. In our case, it will be 10 plus 20 divided by 2, which is 30 over 2, 15 minutes. Okay, that is exactly the midpoint of the interval 10 and 20. What if you want to find the probability that the waiting time is less than, let's say, 12 minutes? How do you find this? Okay, so our distribution is fx 1 over beta minus alpha, that is 20 minus 10, which is 10. Within the interval 10 and 20. So this is how you write the density function. Okay, so the support of x is from 10 to 20. This is the beta minus alpha, that is 20 minus 10. So you have 1 over 10. Right. So let's find this probability. You have to integrate the function fx dx. We need the probability less than 12. The lower limit is 10. So you have to integrate from 10 to 12. So what do you get? 10 to 12, 1 over 10 dx. 1 over 10 is a constant. So you have 10 to 12 dx, which is just x. So you have x over 10 evaluate from 10 to 12. 12 minus 10 is 2. So it is 2 over 10 or 1 over 5, which is actually 0.2. So the probability that the waiting time is less than 12 will be 0.2 or 20%. Okay, likewise, you can find any probability if you know the density function of the uniform distribution. Okay, so similar to that, if you want, you can find, let's say, the probability that the waiting time is in between, let's say, 10 and 15. Between 10 and 15. How do you find it? You integrate from 10 to 15 fx dx. Our fx is 1 over 10 dx. Okay, so 1 over 10 is the constant. You have x, evaluate from 10 to 15, which is 15 minus 10 is 5 over 10, which is exactly the 50%. What does that mean? Okay, even without doing this calculation, you should be able to see that this probability is 50% or half. Why? Because that is the midpoint. Here's our 10, here's our 20, here's our the uniform distribution 1 over 10. You know the midpoint. Here's the 15, right? So you need the probability. This probability. If the total probability is 1, if you have only half of it, so you get the half of 1, which is 50%. Okay. So likewise, you can easily calculate the probabilities when you have uniform distribution. Uniform distribution is the easiest and the simplest one that you can find in continuous random variables. Next, we move on to the gamma distribution. We say a random variable x has a gamma distribution, and we refer to it as the gamma random variable if the probability density is given in this formation. You do not have to memorize this formula, because if you have to do a calculation, these formulas will be provided to you. So you don't have to memorize these equations. We do not expect you to memorize these equations, but you should know how it performs and what are the parameters and how to use these parameters in the proper way. Now let's look at this function. Look at the support. Support of x is greater than 0. That means all positive values of x. Okay, in your number line, all positive values will have the support of x. And it has two parameters. They are the beta and gamma. You can see it in the function also. So x is the random variable. You have semicolon, alpha and beta. These are the two parameters. These parameters will define the shape and the location of the gamma random variable. Okay. So alpha and beta are called the shape parameter and the location parameter, and both of them are greater than 0. Now if you look at this equation, you see 1 over beta to power alpha, so that will be a constant, and you have something called this gamma alpha. What is this? This is called the gamma function. This is called the gamma function. Let's look at this gamma function in detail later. Okay, first let's look at this function. Then you have the random variable x to the power alpha minus 1. Then the exponential part of the gamma distribution e to the power negative x over beta. So you can guess about the shape of the gamma distribution. It is a skewed one, only the positive values of x, and it will look like this. Okay, depending on the value of alpha and beta, you will end up with different types of skewed distributions. Okay, depending on the values of alpha and beta, you will get different shapes and the location for your gamma distribution or your random variable x. Okay, and it is always the e to the negative, so you have the exponential decay. Okay, let's look at this gamma function in detail. Again, you do not have to memorize this, but I will show you how this gamma function works. The gamma function is the integration of t x minus 1, that is the power e to the negative t dt. So t is kind of our let's use x here in order to explain it. Okay, gamma of x is the integration of t to the power x minus t e to the negative t dt, and the support is from 0 to infinity. So this integration is called the gamma function. There are very nice properties that we can look at in a gamma function. The gamma function at 1 is exactly 1. Okay, you can easily prove this. And also the gamma function at, let's say, alpha is, usually use alpha minus 1 in order to explain it easily. Okay, so let's do that. The gamma function at alpha plus 1 is alpha gamma alpha. Okay, the gamma function evaluated at alpha plus 1 is alpha times gamma function at alpha. Okay, so which means, let's try an example. If you have gamma 3, how do you do that? Now your alpha plus 1 is 3, which means alpha is 2. So this is same as 2 plus 1. So gamma at 3 is same as 2 times gamma 2. So you can see that it goes one value decreasing again and again. And gamma 2 is what? Gamma 2 is 1 plus 1. So you get 2 times 1 gamma 1. We know from the definition gamma 1 is 1, so the answer is 2. Okay, let's try another one. What will be gamma 5? Now let's expand this. Gamma 5 will be 4 times gamma 4. But gamma 4 will be 3 times gamma 3. Now gamma 3 will be 2 times gamma 2. And gamma 2 will be 1 times gamma 1, which is 1. So what do you have? 4 times, 3 times, 2 times 1, which is exactly 4 factorial. So what does that mean? In general, you can say that gamma at alpha is alpha minus 1 factorial. See, always one value decrease. Gamma 5 is 4 factorial. Gamma 10 will be 9 factorial. Gamma 20 will be 19 factorial, and so on. In addition to that, you can show that gamma at 1/2 or 0.5 is square root of pi. Okay, so these are some nice properties of the gamma function. Okay, so these are some extra information you need, right? Okay. Now let's see how to derive the mean and the variance of the gamma function. In order to do that, we are going to use the moment generating function, okay, or the information about the moments, because if you look at this function of the gamma distribution, it is kind of complicated. So integrating it to find the expected value and the variance in the usual definition, that is xfx dx, and evaluate from 0 to infinity, it is going to be a little bit hard. Therefore, we use this theorem, the rth moment about the origin, okay, which is defined as mu r prime, that is beta to r gamma function evaluate at alpha plus r over gamma at alpha. Okay, let's try to prove this one. And then we can easily use this theorem 6.2 to evaluate the mean and the variance of the gamma distribution. Okay. So let's do the proof. We have mu r prime, which is exactly the expected value of x to the r. That is the rth moment about the origin, which is 0 to infinity x to the r 1 over beta to alpha. So I'm writing the gamma function, the gamma probability density. Okay, here's the gamma probability density. Again, you are not required to memorize this. Okay, but if you specialize statistics, 300 level, 400 level, you will see this function a lot, and eventually you will memorize it. But we do not ask you to memorize them in 100 level. Okay. Right. Now you can see that there are a lot of constants that you have in this function. But in order to make this integration easy, we are going to do a substitution. Okay, so we do this substitution, which is we replace x over beta by another dummy random variable y. Okay, so we represent y, our new random variable y is x over beta. So we are going to reform this equation, the whole thing. If you have y equals x over beta, that means your dy is dx over beta, right? So you have to do that replacement also. And when x goes to 0, y will also go to 0. When x goes to infinity, y will also go to infinity. So the limits will remain same. Now, in order to combine x and beta, you have to have the same exponent terms. Okay, so x has r and x has alpha minus 1, but beta has only alpha. So let's reform our integration. Okay, anyway, let's take this gamma function outside because it's just a constant. Okay, so what I'm going to do is, since we need extra terms for beta, that means we need beta to power r, otherwise we cannot combine x and beta. Okay, so let's multiply and divide the whole expression by beta to r. So it is like we multiplied by 1. So nothing has changed. Okay. And then we need beta alpha minus 1. So I'm going to write this as beta times beta alpha minus 1. Okay. So this is same as beta to the power alpha. Right. Just took one beta outside. Okay. So beta to 1 and beta to alpha minus 1, you get beta to alpha. And we have the rest as it is. Okay, so if you cannot understand this, go over this again and again. Okay, and then you will be able to understand it. Okay, so now we have, what do we have here? This extra beta to r, I'm going to take it outside. Okay, this br. Then we have our x terms are x, r plus alpha minus 1. And beta also we have the same thing. We have extra beta, we'll write it later, but beta also we have r here. And then we have alpha minus beta. And we have extra beta here. And then we have already wrote x. So the rest is e to the negative x over beta dx. Okay, now we are all set to replace x over beta by y. Now what will happen? Beta to r gamma over alpha, that is gamma of alpha, it's there. Now we changed our variable, the limits will remain same. Instead of x over beta, this is the same power, so we end up with y to the power alpha plus r minus 1. I just changed the positions of alpha and r. Then we have e to the negative x over beta is y, so e to the negative y. And instead of dx, we need instead of a dx over beta, we can write dy. Okay? So we have everything in y terms now. Okay. Now if you look at this integral, this is exactly the gamma at r plus alpha. Okay. So if you go to the gamma function, I showed you here the gamma function. Okay. So look at this function and compare it with what we have here. From that, you'll see that this is exactly the gamma function at r plus alpha. Therefore, our mu r prime is beta to r. This is beta to r we have outside the integration, gamma alpha, and we have gamma at alpha plus r. So this is what we wanted to prove. Okay. Right. So we have mu r prime as beta to r gamma at alpha plus r divided by gamma alpha. So that's the proof done. Now using this expression, you can easily find mu and sigma square. Okay, let's try it. What is mu? Mu is the first moment. At mu, you have r equals 1. So what do we get? Beta to 1 gamma at alpha plus 1. Our r is 1 and gamma alpha. So what is that? Beta times gamma alpha plus 1 is, you already know, that is alpha gamma alpha divided by gamma at alpha. So this cancels out. You get nicely alpha times beta. So this is the mean. So I'll leave as an exercise to find the variance. Okay. So the variance, again, you have to use the computational formula, which is ex square minus ex whole thing squared. You already have this. Okay. So we can square it, but ex square, that is the second moment about the origin. So let r equals 2 and find mu 2 prime. Okay, and find this value using the theorem. Okay, this expression, and then use it in your computation formula, and you will be able to find the variance, which is sigma squared, and you'll be able to find that it is alpha beta square. So I will leave it as an exercise for you. Okay. Although we are not going to do any calculations based on the gamma distribution, because this finding the probabilities is not easy with the usual form of the gamma distribution. But here are some applications. This goes with the Poisson events. I hope you can remember the Poisson distribution that we discussed in chapter 5. If there are Poisson events that occur with the constant rate of lambda per unit time, so that is the parameter of the Poisson distribution, or the rate lambda per unit time. If we define a random variable y as the waiting time for the rth event, okay, so y is the waiting time for the rth event, then this y has a gamma distribution with parameters r and lambda, where lambda is the Poisson rate, and you can express it in this given formation. Okay, and also the moment generating function of the gamma distribution is given there. Again, you don't have to memorize them. If they were needed, they will be provided. Okay, so we learned about the gamma distribution because it is very useful when we define the exponential distribution. That is our third density function. Exponential distribution is widely used compared to the gamma distribution, because in our day-to-day life and in many research topics, we end up with random variables following this exponential distribution or this exponential decay. Therefore, exponential distribution is a very famous and widely used distribution function. It is a special case of gamma where alpha is 1 and beta is theta. So that is why we learned about the gamma distribution in the first place. Okay, so again, the exponential distribution is a special case of gamma density where alpha is 1 and beta is theta. So if you substitute alpha to be 1 and beta to be theta, you will get this definition 6.3. Here's the exponential distribution. It has only one parameter. Since alpha is 1, you have only one parameter called theta, and the support of x is again the all positive integers or the positive number line, and this parameter theta is always greater than 0. Okay, so here's the exponential density, and when x follows exponential density, we write it as x follows exponential with the parameter theta. So this is how we express the exponential random variable. Okay, now we have to find the mean and the variance of the exponential distribution. Now you can see the pattern. Always when we define a distribution function, we try to find the mean and the variance, right? Because they are very useful in statistics. And then we see how we can calculate the probabilities, and if you need other moments. Okay, so let's try to find the mean and the variance of the exponential distribution. Now this is little bit tricky because you need the knowledge of integration by parts. I assume that you have learned integration by parts now. You have learned it in your advanced level classes also, and even in mathematics courses in the first semester. So you need the knowledge of integration by parts. If you cannot remember it, please refer it, go back and look at your notes in mathematics and get familiar with the integration by parts. Okay. First, let's try to find the mean, which is the expected value of x. Okay, so we write the definition: x fx dx. Support of x is the integration. Our support is x greater than 0. So it will go from 0 to infinity. X times fx is 1 over theta e to the negative x over theta dx. 1 over theta is a constant, so let's take it outside. And our integration is from theta to infinity x e to the negative x over theta dx. Now this is where you need the knowledge of integration by parts. Okay. So what do you need? The integration part is u dv equals uv minus v du. So we have to find what is u and what is v. So in this case, we define our u to be x, and then our dv will be the rest, e to the negative x over theta dx. So which means du will be simply dx, and our v will be with this negative theta e to the negative x over theta. Okay, so how do you figure out which is going to be u and which is going to be dv? There are several methods you can find. One possibility is, here's a trick. Let's say this is Lal is always eating tomatoes. Okay, this is a nice way to remember. Okay, I'll explain what is this. L is for log, I is for inverse, trig, A is for algebraic, E is for exponential, and T is for trig, the trigonometric functions. Okay, so L is for log, I is for inverse trig, that is like sine inverse, cosine inverse, tan inverse, and so on. A is algebraic. Algebraic means just x square, x to the 3, and so on. E is the exponential, e to the power, and T is the trig function, sine, cos, theta, sec, and so on. So what do you see? What you have to do is you look at these functions and try to find whether there are log functions, whether there are, first you find whether there's a log function. If there's a log function inside your integration, that will be your u. Now in this one you don't see any log function. Then you go to the next one. Next is the inverse trig, and you don't see any inverse trig function here also. So you go to the next one, which is the algebraic. There is an algebraic one. This is x, just x. If you have x square, it will be the algebraic function. So you choose u to be x, and the rest will go for dv. If you didn't see any any algebraic function, then you go for the exponential. Okay, but we have the algebraic function here, so we use it as u. So if you can remember this, Lal is always eating tomatoes, you know how to find u. Okay, you go over this in order. Okay, if there's a log 1, that will be u. If not, you check whether if there's an inverse trig. If not, you go for algebraic. If not, you should check for exponential. If not, the last one is the inverse trig. Okay, so that is how you figure out what is u and what is du. This is one way. Okay, now we have du and dv. We have u and dv, so you have du and v. Now let's apply it to our function. Okay, we have is 1 over theta. Okay, so remember that you have 1 over theta. We will come to that later when we find the final answer. Okay, so our u dv is just the integration, right? So u is x, v is negative theta e to the negative x over theta. Evaluate from 0 to infinity minus integration 0 to infinity. V is negative theta, so this negative and this negative becomes plus theta e to the negative x over theta du is dx, right? So here's our v and du is dx. Okay, now what will happen to this first term? When x is 0, this whole term goes to 0. When x is infinity, you have 1 over infinity from this term. So 1 over infinity is also 0. So this whole term goes to 0 in either situation. So we end up with only the second term. So what do you get? We have theta here, and then the antiderivative of e to the negative x over theta is again we have theta, right, with the negative sign. We have negative theta. Okay, right, so evaluate this from 0 to infinity. So you have negative theta squared e to the negative x over theta, evaluate from 0 to infinity. So what do we get? Get negative theta squared. When x goes to infinity, you have negative 1 over, so negative x over infinity means 1 over infinity. So that is 0, and e to the 0 is 1. So we end up with theta square. So the integration parts gives you theta square for this integration, which means our ex is now, we have this 1 over theta, and from integration by parts we found theta square. So 1 theta will go on. So we get our expected value or mean is the theta, right? So that is the proof of the mean of the exponential density. Okay, now in order to find the variance or sigma square, okay, so again I'll leave it as an example for you. In order to find the variance or the sigma square, again you can use the computational formula. Again you have ex, which is theta, so you have theta square here. Ex square is you have to find the expected value of x square, which is 0 to infinity x squared 1 over theta e to the negative x over theta d theta. Okay, so which means you have to use integration by part twice. Okay, you have to use integration by part twice. When you do once, you will end up with the ex again, this term again. So you do it the integration by parts again, and you will be able to find a value for ex square. So try it by yourself and use it in the computational formula. You already have ex square. You can find the value of sigma square, and you'll find that it is theta square. Okay, so try it by yourself. Now if you refer statistics textbooks, you'll find an alternative formation of the exponential distribution. So this is an alternative equation. I'm mentioning it because if you see this in textbooks and you will get confused. Okay. So here's another way of expressing the exponential density. Rather than using 1 over theta, we use lambda. Okay, so 1 over theta replaced by lambda. So you have lambda e to the power negative lambda x. That is an alternative form, but it's the same thing. Okay, it's the same thing. Instead of 1 over theta, you have lambda. In that case, your mean will be 1 over lambda, and variance will be 1 over lambda square. Okay, it is only the difference between the term mean and the rate. Okay, but in this course, we'll stick with this given equation in the definition 6.3. But if you refer other textbook, if you see this formation, this alternative formation, don't get panic. This is another way of writing the exponential density. Okay. Right. Let's go back to the lesson. Shall we try to find the CDF of the exponential distribution? Okay. What is the CDF? That is the cumulative density function, capital Fx. How do you find it? By integrating from the lower support of your random variable up to any x fx dx. This is the definition of the CDF. That means you find the probability of the left tail up to a certain value x. Okay, let's try to find the CDF of exponential density. Capital Fx is the lower limit of x is from 0, 0 up to x. The exponential density is 1 over theta e to the negative x over theta dx. Okay, 1 over theta, let's take it out, and you get negative theta e to the negative x over theta evaluate from 0 to x. So this is the antiderivative. So this theta and this theta cancels out. You have negative sign outside, this negative sign, and evaluate e to the negative x over theta from 0 to x. What do you get? You get negative e to the negative x over theta minus e to the 0. E to the 0 is 1. Okay, so you get negative e to the negative x over theta minus 1. This minus and this minus, you get 1 minus e to the negative x over theta. So here's the CDF of exponential density. Okay, this is the CDF of the exponential density. Okay, so it is 0 when x is less than 0, and it attains 1 when it goes to infinity. Now, when you calculate probabilities using exponential density, you can either use the CDF, I'll show you, because it is very easy, rather than integrating all the time. Okay, let's look at some applications of the exponential distribution. Now, suppose you have Poisson events occurring at a constant rate of lambda per unit time. If we denote y to be the waiting time for the first event, right? Now, compare this with the gamma. In the gamma distribution, you have the waiting time for the rth event. Now, here we are looking at the waiting time for the first event. Then we say y has the exponential distribution with parameter theta. Okay. So, usually the waiting times, the decays, the mortality rates, those can be nicely modeled using exponential distribution. Okay. Another example is the time of electric bulb. So if you draw the exponential density, it will be like this. Depending on the value of theta, the slope will be different, right? So this is how the exponential density will look like. Here's an example. Okay. Now suppose x follows exponential density with theta equals 3. Okay, a simple example. You know that the random variable x follows exponential with theta equals 3. Now, shall we write the PDF? Fx is 1 over 3 e to the negative x over 3. The support of x is greater than 0, 0 whatever. This is how you write the PDF. Now, what is the mean? mean is theta, which is 3. The variance is theta square, which is 9. Right? So, very easy. When you know the mean and the variance, you know what are the values. Now let's try to find the CDF of this one. What is the CDF? You already know the equation. Here's the CDF, 1 minus e to the negative x over theta. So that will be 0 when x is less than 0. 1 minus e to the negative x over 3. This is the CDF, right? Now let's try to find some probabilities. The first one is, let's try to find the probability that x is greater than 4. Now remember, x is continuous, so writing x greater than or equal or greater than equal or greater than 4, both are same, because the point probability is 0. The point probability is 0, so writing x greater than or equal to 4 or x greater than 4, they are the same. Now remember this thoroughly. For discrete case, these two are not same, because for discrete case you can find point probability. For example, the binomial distribution, you can find probability x equals 3 or something like that, right? It has a probability value. But when it comes to continuous case, because it's a smooth function, you cannot integrate a point. Okay, if you integrate a point, you'll end up with 0. So the point probability is 0 for continuous distributions. Now I'll note it down somewhere, okay, so you won't forget it. Point probability is 0 for continuous random variables. I already mentioned this in chapter 2, I guess. Okay, but remember that thoroughly. Okay, only for continuous. Now, how do you find x greater than 4? You have to do the integration greater than 4. So 4 to infinity fx dx, which is 1 over 3 e to the negative x over 3 dx. Okay, so what do you get? 1 over 3 is a constant. Have e to the negative x over 3, and the antiderivative you multiply by negative 3, integrate from 4 to infinity. So this 3 cancels out, you have negative value outside, and you get e to the negative infinity is 1 over infinity, which is 0, minus e to the negative 4 over 3. So what do you get? Negative and negative cancels out. The answer is positive e to the negative 4 over 3. You can easily find the exact value of this one using a calculator. Okay, plug in this we have the e to the function in a calculator to the power negative 4 over 3. You can find the answer. Now, is there another shortcut that you can do this? What is px greater than 4? Px greater than 4 is same as 1 minus px less than 4, which is by definition the CDF at 4. So 1 minus, you have the PDF, 1 minus e to the negative 4 over 3. 1 and minus cancels out, you end up with e to the negative 4 over 3. See the same answer. Right? So if you want to find probabilities, you can use either the CDF or you can do the hard way, integrate again. Right? Now what if you want to find the probability, let's say x is in between, let's say x is in between 1 and 6. How do you find this one? 1 and 6. Either you can integrate from 1 to 6 fx dx, right? You can do the integration 1 to 6 fx dx, or you can use the CDF. This is same as f evaluate at 6 minus f evaluate at 1. Okay, this is same as f evaluate at 6 minus f evaluate at 1. Okay, and you have fx. Okay, you can easily find it. F evaluate at 6 is 1 minus e to the negative 6 over 3 minus 1 minus e to the negative 1 over 3. Right? Again, 1 and 1 cancels out. You'll end up with e to the negative 1 over 3 minus e to the negative 6 over 3. Right? So this will be the answer, and you can plug this value into a calculator and find the answer. Okay? Right. I hope now this is clear how to find the probabilities for an exponential random variable. Let's try another example. Students arrive at a local bar and restaurant according to an approximate Poisson process at a mean rate of 30 students per hour. Okay, you have to be very careful with the units. It says 30 students per hour. Now look at the probabilities you want to calculate. What is the probability that the bouncer has to wait less than 3 minutes to card the next student? Okay, you know the bouncers waiting at the restaurant. Okay, if there are students or if there are people who want to enter but the bouncer is refusing, then they issue a card, so they say you cannot enter, right? So likewise, the bouncer has to wait, okay, the next customer, and the next one, and so on. So you want to find the probability that this bouncer has to wait less than 3 minutes for the next student. And if you go to part B, it is to wait more than 4 minutes for the next customer, and so on. Okay. Now, before we start calculating, you have to identify correctly the distribution of this scenario. So you have the approximate Poisson process at a mean rate of 30 per hour. Okay, it says for the Poisson, so this is the Poisson rate. Okay, now you have to go back and look at that applications I show you for the exponential. It explains how this Poisson process is related with the exponential density. Okay, so the Poisson rate is 30 per hour. 30 per hour. What does that mean? Per 1 hour, now these questions are in minutes, so you have to convert hours into minutes. So you know 1 hour is 60 minutes. So the Poisson rate is 30 per 60 minutes. Okay, 1 hour is 60 minutes, so we converted our rate from hours to minutes, because in all these probabilities they are asking in minutes, 3 minutes, 4 minutes, so you cannot keep the rate in hours. You have to have the same unit. Okay, so 30 per hour means 30 per 60 minutes. That means, what is it per minute? You divide 30 by 60, so that is 1 over 2 per minute. Okay, so 30 per hour means 1 over 2 per minute. Okay, so we can define our waiting time x. X is our waiting time. Okay, and it has our random variable is x, and for the exponential density we need theta. So theta is our Poisson rate, because it's the mean rate. So you have 1 over lambda, okay, which is 2 minutes. Okay, why? Okay, if this is confusing, you can easily see this is our theta is what? 1 over 2. So this 1 over 2 is exactly our theta. Okay, if it's confusing with this lambda, just look at our the theta value. Okay, sorry, the theta lambda is 1 over 2, so our theta is 2 minutes. Okay, right. I'll explain it again if it's confusing. Our 1 over 2 per minute is the Poisson rate. Poisson rate is related to our exponential theta, as theta equals 1 over lambda. Okay, right? Okay, so the lambda is 30 per hour, or this 1 over 2 per minute. Okay, so you have lambda is 2, which which means 1 over lambda is theta, which is 2. Okay. So again, the Poisson rate is 30 per hour or 30 per 60 minutes or 1 over 2 per minute. Okay, so our lambda is 1 over 2. Therefore, 1 over lambda is 2. That is exactly our theta. Okay. So what we get, the Poisson rate is lambda, but 1 over lambda is theta. So therefore, theta is 2. Therefore, we can write our fx as 1 over theta is 1 over 2 e to the negative x over 2 x greater than 0, 0 otherwise. Okay. So here's our exponential density. Now we can find the probabilities. What is the probability that the bouncer has to wait less than 3 minutes? So the probability x less than 3. Okay, what you have to do is integrate from 0 to 3, 1 over 2 e to the negative x over 2 dx. Right? So you have 1 over 2 e to the negative x over 2. You have negative 2. Evaluate from 0 to 3, 2 cancels out. Have negative value outside. You have e to the negative 3 over 2. Evaluate at 3 and minus e to the 0 is 1. And with the negative sign, you have 1 minus e to the negative 3 over 2. And this is exactly the f3, right? This is exactly f3. Again, you can plug in this e to the negative 3 over 2 to calculator and get the exact number. And do 1 minus, you can find the probability value. Let's try the next one. What is the probability that the bouncer has to wait more than 4 minutes? More than 4 minutes, greater than 4. Now, if you want, you can go for the CDF, right? What is the CDF? 1 minus e to the negative x over 2 is the CDF. So, use it here. You get 1 minus e to the negative is 1 minus f4, right? So f4 is 1 minus e to the 4 over 2, so which is e to the negative 4 over 2. Again, you can plug it into the calculator and find this easily. Now we have, that is the probability that the bouncer has to wait 2 to 5 minutes. Again, you can do this in 2 ways. The first way, the harder way, 1 over 2 e to the negative x over 2 dx. Evaluate from 2 to 5. Or this is same as CDF at 5 minus CDF at 2. Okay. This is 1 minus e to the negative 5 over 2 minus 1 minus e to the negative 2 over 2 which will be 1 minus 1 cancels out and the negative becomes positive e to the negative 1 minus e to the negative 5 over 2. Right? Find the exact value using the calculator. Or even if you leave your answer like this in an examination, that is also fine. This is acceptable. So you don't have to simplify it. If you leave the answer like this, that is also okay. Right? Right. So that is about the exponential distribution. So we learned about the uniform distribution, the gamma distribution, and a special case of gamma, which is the exponential distribution. In addition to that, there is another distribution called the beta distribution. We are not going to look at it. It's another skewed distribution, very similar to beta, which contains the gamma function, but we are not going to talk about in detail here. But we move on to another important distribution in statistics, which is called the normal distribution. Normal distribution or the Gaussian distribution. This is called the Gaussian distribution because this was introduced by the German mathematician Carl Friedrich Gauss. Okay, this was introduced by the Carl Friedrich Gauss, or C.F. Gauss, in 1809. Okay, so in order to honor him, we call the normal distribution as the Gaussian distribution. Now, the normal distribution is the key distribution in statistics, because most of the theories are developed assuming that the random variable follows the normal distribution. Okay, the reason is, if you consider a huge amount of data, that means if you think about a population, usually the averages, they have this normal distribution. You learn about these special characteristics in your 200 level courses in detail, but until then, know that in most of the situation in the real world, you can model most of the variables using the normal distribution. Most of the variables, when you have large number of observations, you can approximate or you can model them using the normal distribution. Therefore, a lot of theories in statistics are derived and proved assuming your random variable is a normal distribution, or it follows the normal distribution. So we'll talk about the behavior and shape of the distribution in detail later. Okay, but knowing that your data follows the normal distribution is kind of very nice thing, and your life becomes very easy if you know that your data set follows a normal distribution, because most of the theories, most of the models derived in statistics can be used without any difficulty when your data set is normal. Okay, so that is why we say normal distribution is the most famous and widely used distribution in statistics. Now let's look at the density of the normal random variable. A random variable x has normal distribution if it has the PDF given in this form. Now you can see this function. It is not easy. It is kind of complicated, like the Gauss distribution. Okay. So calculating probabilities using this PDF, it's hard, and we do not do that because we have another easier way to do that. Anyway, the support of your random variable xv will be all the values from negative infinity up to plus infinity. That means the whole number line. And you can see that there are two parameters, that is mu and sigma, which is exactly the mean and the standard deviation. You can see the variance at the bottom, and you can see the mean mu and variance again at the top under this exponential negative term. Okay. The normal distribution, it looks like this. It is a nice bell-shaped symmetric distribution. Okay. It is symmetric about the mean mu. It is symmetric about the mean mu, and the thickness or the fatness of this curve will be decided using your variance or the standard deviation sigma. Okay. So mu is called the location parameter, and sigma is called the shape parameter, because it will define the shape of your bell. Okay, so this bell is symmetric about mean, that means exactly half of the data will fall in the left tail and exactly half of the data will fall in the right tail. You know, the total probability is 1, so this area under the curve. Okay, so this total area under the curve is 1 or 100%, which means each side contains 50%. Okay, to the left of the mean and to the right of the mean, because it is symmetric about the mean. Okay, so for example, if we say random variable x follows normal distribution with mean 5 and the standard deviation 2, your bell will be symmetric about 5. Okay, here's the location. And suppose you have another random variable, let's say y follows normal distribution with mean 10 and sigma 2. What does that mean? The fatness of the bell will be same, but it will be now shifted to 10. Okay, the same shape, but the location is shifted right by 5 units. Now suppose you have another distribution, let's say W, again normal, mean 5, and the variance, let's say 4. The standard deviation 4. How will this look like? Now you have a large variability, so the bell should be very fat and it will be flattened. So still symmetric about 5, and it will look like this, right? A flat bell. Okay. And let's say another one, say Q follows normal distribution with mean 10 and sigma 1. Now the variance or the standard deviation is smaller, but the location is still 10. So your graph will look like this, right? So your bell is now very thin, but still symmetric about 10. Okay, so likewise you can figure out the location and the shape of the bell of your normal distribution depending on the mean and the variance. Okay. Now there are some theoretical content here. Now this variance, the variance is also always 0, the standard deviation is always 0. Therefore, the values that you can get for the normal distribution, they are always positive. Therefore, if you want to show that this is a proper probability density function, the first condition is satisfied. The next should be the area under the curve should be equal to 1. You can check that by using this substitution. We substitute x minus mu over sigma, that is this quantity you see in exponent, by another variable z. Okay, and then after doing the change of variables, you can write the original PDF in form of dz or dz. That will be 1 over square root of 2 times pi, and the integration becomes much more simpler now. Okay. Now another substitution with z square over 2 to be y. You can find the gamma function hidden inside this one, which is square root of pi divided by square root of 2, because gamma 1 over 2 is square root of pi. Okay. And then if you go back, right, you'll find that you exactly get the value total probability 1. Okay, so I'm not going to do this proof again, but you can go over these steps and identify the answer or understand the answer, because you already know about the gamma function and you are familiar with this change of variables and substitutions. Okay. Again, you are not required to memorize these equations. Okay, you are not required, but eventually you will memorize, because you are going to use the normal distribution a lot. So usually at the end of the second year, automatically you will memorize the normal distribution. Okay, you will memorize the normal distribution eventually. And then we get the moment generating function of the normal distribution, right, given in theorem 6.4. Again, the proof is there. You can go over it leisurely and try to understand it. Okay. And here's an exercise also. Using the moment generating function, you can derive the parameters mu and sigma. Right. Now let's look at some practical uses of the normal distribution. Exam scores of students in a class is normally distributed with mean 80 and standard deviation 8. How do you explain this? Exam scores of students in a class is normally distributed with mean 80 and standard deviation 8. So our random variable x is exam scores. It says x is normally distributed with mean 80 and standard deviation 8. Okay, so if you draw the curve, nice symmetric bell curve, it is symmetric about the mean 80 and the standard deviation is 8. Okay. Now, what if you want to find the probability that the percentage of exam scores greater than 90, or in other words, this is the percentage of students who scored the score greater than 90. Okay, so I want to find this. So you want to find the probability a student get a score greater than 90. How do you find it? Where's 90? 90 will be somewhere here, right? You need greater than 90. So you need this area under the curve. That is the probability, right? Another one. What is the probability that the exam scores, or the probability that the student get the exam score, let's say less than 50. Less than 50. How do you find this probability? 50 will be somewhere here. Less than 50 is this left tail. Okay, so this is called the left tail. Now remember, in normal distribution, these tails are very, very thin. Okay. So when it goes to far away values, the normal distribution, the tail probabilities, they will be approximately 0 when it goes to plus infinity and negative infinity. Okay. So the tail probabilities will approximately 0. Okay, I'll show you again when we do calculations. And also you should be able to find what is the probability that a student gets the result, let's say 75 up to 85. How do you find this? Okay. So here's 75, here's 85. So in between this area under the curve of this in between area, red colored area, how do you find this? Now you know that the PDF of the normal distribution, it is this complicated equation, right? This complicated equation. Now integrating this equation from 75 to 95 or 95 up to infinity, it is doable, but it is not practical. It is hard actually. And normal distribution is used by many people and many researchers who are not just mathematicians or statisticians. So we do not expect that they know these hard calculations in integrations. Okay, the sociologists, the economists, the politicians, everybody will be using the normal distribution, the biologists, everybody. So we cannot assume that they all know how these hard integrations are done. Therefore, we have a nice way of doing these calculations using something called the standard normal distribution. Okay, that means any normal random variable can be represented as a standard normal distribution. That means any random variable having a normal distribution with any mean mu, any standard deviation sigma, can be transformed into a standard normal distribution. After you standardize, you can read a standard normal table. There is a table available with the probabilities already calculated for you. So when you know how to read the table, you can easily find the probabilities. And those who have done mathematics in A levels, they have already used this table. Okay. Anyway, we are trying to refine your memory. Okay. Now, how do you standardize? How do you transform your normal distribution to standard normal distribution? So that is called the standardization of finding the z-score. How do you find the z-score? You take your random variable x, whatever the value, subtract the mean, divide by the standard deviation, you get the standardized value. Or what do you call as the z-score? And you know what the z-score is, because for your advanced level examination results, you get your own z-score, and this is how it was calculated. Okay. Now, when you know the z-score of a certain x random variable, you can easily calculate the probabilities by reading the standard normal distribution table. Okay. Now we have the proof of this standardization. Again, I'll leave it for you to study. Again, you do not have to memorize them, or we do not require you to memorize these proofs. Okay, but this is just for your knowledge. Okay. So therefore, you can use a standard normal table after you find the z-score of any random variable x which follows a normal distribution with any mean or any standard deviation. Okay. So here's the standard normal distribution table. Now there are a few things that you should know about this table. Okay, this is a part of the table. Usually you have two pages. One is with the z-scores negative values, one is with the z-scores positive values. But in this course, we show you how to read only the positive values, because that is enough. Even the negative values, you can use these positive values and find the probabilities. Therefore, we only look at the page where you have positive z-scores. Okay. First, let's look at how this standard normal curve looks like. The standard normal density is a normal distribution with mean 0 and standard deviation and the variance both 1. Okay. So, your x is normal with any mean mu, any standard deviation sigma, but after you standardize it, x minus mu over sigma, this z will follow a standard normal distribution, which means you have a 0 mean and standard deviation 1. Now, if you draw the bell curve for the standard normal distribution, it is symmetric about the mean, which is 0. So you have all negative z-scores and all positive z-scores to the left and to the right, respectively. And towards the tails, you will get very small probabilities. So therefore, especially after negative 4, negative 4.5, positive 4, positive 4.5, and beyond that, the tail probabilities will become very, very small, approximately 0. So these tails, the tail probabilities will be approximately 0. Okay, right. So let's go back to our standard normal distribution. Now what do you see here? You see Z. Okay, you see the letter Z, and the first column you see it start from 0, 0.1, 0.2, 0.3, and so on. It goes up to 0.4, because beyond that you won't get much values. Those are the tails. Okay, those are the tail probabilities. And then from left to right, what do you see? You see 0, 0.01, 0.02 up to 0.09. These are the second decimal place of your z-score. Second decimal place. So usually we round up to second decimal place after you calculate this z-score. After you calculate this z-score, we round it up to 2 decimal places. Then only we can read the table. Okay. Right. The other important thing is this table will give you the probability of the left tail. Okay, probability of the left tail. So here is z0, this 0, 0.0. What is the probability? 0.5. That is, this whole tail is 0.5. That is the 50%, because it is the midpoint. Okay, by symmetry you have 50% to the left, 50% to the right. So the other half will have the other 50%. So altogether you have 100%, or the total probability 1. Okay, so again, when you say z-score 0.0, under that you have the probability 0.5. That means the probability from the left tail up to the value 0, this whole left tail is 0.5. Okay, let's try another one. I have the z-score somewhere here, which is 1.23. My z-score is positive 1.23. How do you find it? You read 1.2 from the first column. See, here's 1.2. Can you see that? Here's 1.2. And you read the second decimal point from the next column. So we need our second decimal point is 3. So 0.03 here. So you go along 1.3 and you come down 0.03 here. So what is the probability? 0.89065. So area under the curve to the left of Z score 1.23 is 0.89065. So how do you write this probability? Z less than 1.23. Again, less than or less than equal, that doesn't matter. Okay, so the Z score 1.23, 1.2 from the first column and the second decimal place from the next columns to your right, and you go along 1.2 row until you come under the second decimal point. And where they cross, you get the probability of the left tail. Let's try another one. I want the probability of the Z score 1.80. 1.80. How do you find that? 1.8, you find it from the column. So here's our 1.8. And what is our second decimal place? Our second decimal place is 0, so it's the first column. So you stop from here. What is the probability? 0.96407. So the left tail all the way up to 1.8, that probability is 0.96407. So probability Z less than 1.8 is this 0.96407. Okay, I hope this is clear. Now what if you want this other right tail? What if you want this greater than side? What is the probability Z greater than 1.8? How do you find that? You use the complement. This is same as 1 minus probability Z less than 1.8. So you know the probability Z less than 1.8. So you get 1 minus 0.96407. So that is how you find both the left tail and the right tail probability. Okay. Now let's move on to another example. Here's the part of the table again. What if I want the in-between? Okay. What if I want the in-between? I want the probability. Here's the 0. I want probability 0.22 up to say let's say 5, 6. Okay. I need this in between area. How do you find this? Okay, if we read 0.22, what do you get? Here's 0.2. Here's 0.22. Right? So there's the probability. So that is the area to the left of 0.22. What is that area? This area. Okay. Then we read the area of 0.56. Yes, 0.56. What is that probability? 0.5 and 6. Right? So you go along 0.5 until you come under 0.06. What is that area? 0.7123. So you have this whole left tail up to 0.22, it's 0.5871, and the tail area to the left of 0.56, 0.7123. Now what do you want? You only want the difference in between 0.22 and 0.6. So here's 0.22 somewhere here. What we need is only this area. So how do you find that? All the way up to 0.56 you have everything, but you don't want this area, this red colored area. You don't want it. What you want is only this 0.22 up to 0.56. So what do? you have to subtract this unwanted part. How do you subtract it? Because you already know that unwanted part is 0.5871. So how do you find that probability? You get the probability all the way up to 0.56 and subtract the unnecessary area, which is 5871. When you subtract this, you get the area you want. Okay, so the probability in between is 0.1252. Right? So how do you do that? You read the area up to the bigger value and subtract the area from the smaller value. You get the in between. Okay, right. Let's try another one. I want the area from 0.6 and 0.8. In between 0.6 and 0.8. So how do you write it? 0.6 less than is at 0.8. Right? So you read all the way up to 0.8. 0.80. So it is 0.7881. Right? Yes, the one. And then you subtract the unnecessary part, that is 0.60. Here's the one. So you subtract 0.7257. So you get the answer. Right? You can find it. Now we have the problem, what about the negative values? So all the examples that we did, right, they are all positive Z scores. Now what will happen if we get a negative Z score? Okay, so let's try that also. So to the left of the 0, you have the negative values, right? What if I want the Z score negative 0.25? I want the Z score, I want the area to the left of negative 0.25. Now we do not have the negative Z scores in our table, but we know that the normal distribution is symmetric about the mean. Same for the standard normal distribution. This is symmetric about the mean. Therefore, the area to the left of negative 0.25 is same as area to the right of positive 0.25. Okay? Again, area to the left of negative 0.25 is same as area to the right of positive 0.25. This is by symmetry. Now you can see how to find this area. How do you find this right tail? Right? You read Z, so less than negative 0.25, it is same as probability Z greater than positive 0.25. Okay? So how do you get the positive 0.25? You do 1 minus Z less than positive 25. Right? So you read 0.25 from the table. Where is it? 0.2 is here, 0.5 is here. There you go. Right? And you do 1 minus. Right? So that's all. You get the answer. Right? You read up to positive 0.25. You read up to positive 0.25. You get the left tail up to 0.25. But what we want is the right tail. So you do 1 minus. So this is same as the left tail by symmetry. So if this is 0.5987, this is also 0.5987. So that is how you get the negative values. Okay, so that is how you get the negative values. Let's try another example. Now what if you have to find the in between of positives and negatives? So here's the 0. Let's try it nicely. Here's my 0. Suppose you want to find the in between of negative 0.42 up to positive let's say 81, this area. Okay, how do you do that? Now what do you want? You want all the way up to 0.81, no problem, you can find it. All the way up to 0.81 you can find it. Then you have to subtract this unwanted thing. This unwanted area is the area to the left of negative 0.42. How do you find this area? Now you know how to find it by symmetry. Okay, so let's first find this unwanted area. Okay, so what you have to do is you have to read 0.42. Positive 0.42 is there. See, positive 0.42 is 0.6621. Okay, so this area will be 1 minus 0.6621, right? Okay, so this area is 1 minus 0.6621 because here's positive 0.42 this area, right? So this is 1 minus 0.6621. Therefore, negative 0.62, this unwanted tail is also 1 minus 0.6621. And you can easily get 0.81. What is 0.81? Yes, 0.81, 0.71, So the probability in between negative 0.42 and 0.81 is what? Up to 0.1 is 0.7910. You have to subtract. The answer you get from this one. 1 minus 0.6628 is what? 275. 906 is 3. So you subtract 0.3372. Right? So do the calculation and you can find the area you want. Okay? So you do not need the negative side of your Z table, but if it is available, you can use it. But the positive table is more than enough. Okay? Now I guess it is clear how to read the table, the right tails, left tails, in between, negative values and everything. Okay? Now there's another thing that you can do. You can do the reverse also. That means if you know the probability, you can find the Z score. Okay, how do you do that? Now say for example, I know that in my problem for a certain Z score, the area to the left is 0.881. I know that area, but what is the Z score? So this is the reverse. How do you do that? You know the left tail area is 0.881. You have to find the Z score. So this 0.881 should be somewhere in this bunch of numbers. Now you have to find it. This is in ascending order starting from 0.5 up to 1. So find 0.88. Okay. So here's 0.888789. Here you go. 0.881 is here. So what is the Z score? You go to the over the row. It is plus 1.1 plus 1.1, and the second decimal place is 0.08. So it is 1.18. The Z score is 1.18. I guess this is clear. Let's try another one. Okay, so my area to the left is, let's say, 0.95. Area to the left is 0.95. What is the Z score? So you have to find 0.95 in this bunch of numbers, right? You see that 0.95 exact value is not there, but you can find the value which is closest to 95, right? So the two values are 0.94950 and 95053. So which one is the closest? It is 1.65, right? This one is closer to 0.95. It is only this is 53 deviation and this is 50 deviation, so it is this one. So use the nearest one. Okay, use the nearest value. So that will be 1.64. Okay, so likewise you can go for the nearest value. If the nearest values are in the same distance, average it. Okay, so that is how you find the probability, the Z score, if you know the probability. Even the left tail, you can do that by doing the 1 minus. Okay, and then read the positive value, and the corresponding negative z score will be the left tail, right? So you can use the symmetry in that case also, right? Now you know how to read the table, and now you know how to standardize. So let's do an exact example. Exam scores of students in a class is normally distributed with mean 80 and standard deviation 8. So that is the same example we discussed. So our x is normally distributed with mean 80 and standard deviation 8. Okay, you have to find the probability. Here's the normal distribution, greater than 85, greater than 85, this one, right? Greater than is everything above 85. Now how do you do it? First you have to standardize, otherwise you can't read the standard normal table. First you standardize. You find the z score, x minus mu over sigma. So what is the z score? Our x is 85, subtract the mean 80, divide by the standard deviation 8. So you get 5 minus 8. Okay. So here's our z score. When you standardize, it is symmetric about the 0. Okay. So what is the value of 5 divided by 8? Okay, so this will be 0.62. Okay, so 0.62. So you need this area, right? So use the table. You need 62. Here 6, second decimal place 2. Your probability is 0.73237. 0.73237. But what we want is this tail. So it is 1 minus 0.73237. So probability x greater than 85 is same as probability z greater than 0.62, which is 1 minus 0.73237. And you can find the answer. Okay, here's the next one. You need x less than 60. Yes, our 80, 60 is somewhere here. You need the less than, so the left tail. Now standardize it. Find the z score, x minus mu over sigma. You get x is now 60. Subtract 80, divide by 8. You have negative 20 over 8. So what is negative 20 over 8? That will be negative 0.25. So this is same as the left tail of the z score, negative 0.25. That it should be 2.5, right? Negative 2.5. Sorry, negative 2.5. Now how do you find this one? You have to use the symmetry. Left to the negative 2.5 is same as positive 2.5, the right tail, right? So you can read 2.5 is 2.5, it is 2.50, which is 0.99379. So this is 0.99379, 1 minus. So it is same as this side. Okay, so you can find 1 minus 0.99379. So that is your answer. So the probability x less than 60 is same as probability z less than negative 2.5, which is same as the probability z greater than positive 2.5. and that will be 1 minus 0.99379. So you can find the answer. Similarly, you can find the middle also. I'm not going to do that. You can try it. But let's do the last part, part D. You need the 80th percentile of exam scores. Now this is the reverse. What do you know about the 80th percentile? 80th percentile means at that point 80% of data falls to the left of it. Right? 80% of the data falls to the left of that cutoff, the 80th percentile. So you can find the Z score of the 80th percentile, because if you read the probability to the left 80%, so this is 0.8, area 0.8 to the left, and find the Z score, we can use the standardization equation and find what is X, because we know the mean and the standard deviation. Okay, so let's try to find the Z score of 80% or 0.8. Right, so let's try to find 0.8 or a value close. Okay, so here are the candidates for 0.8, 0.799, 0.8023. So what is the closest one? This one has 2-3 deviation and this one has only 5. So the closest will be 0.84, right? See, this is the closest, 0.84. So the Z score of 80th percentile is 0.84. Now let's do the back calculation. This is the Z score. Now we need the exam score, which is X. Mean is 80, sigma is 8. So multiply 0.84 by 8. You get X minus 80. Then X will be 0.84 times 8. You do this to the other, put 80 to the other side, plus 80. So that will be the exam score of the 80th percentile. That means after you find this number, you'll see that 80% of the students got score less than that X. So that is the 80th percentile. Okay, so likewise, you can find X for any percentile. You do the reverse, read the table, find the Z score for the closest probability, and do the back calculation of the standardization, and you can find X. Okay, so that is the normal distribution, and I suppose you got the idea about the calculations, the properties of the normal distribution, and so on. Okay, so that will be the end of this lesson, and as an extension for chapter 6, I will discuss the approximation of the normal distribution to binomial and Poisson in another lecture. Okay, so that is why we said the normal distribution is widely used. Even the discrete distributions like binomial and Poisson can be approximated using the normal distribution. So we will discuss about those approximations in a separate lecture. That will be an extension to chapter 6.